Hello, hi guys. Can you hear me? Just confirm now. I hope now I should be audible. Okay. Okay. Those who are in the stream, just if you can write in the chat so that I know how many people are watching. Will. Okay. Uh, okay. We'll move in sequence only with first, second, third, and fourth. Sorry about that, but if you are in for the third problem, we'll very soon move to the third problem. First and second are quite easy only. So just wait till then. Okay, I think we can start now. Okay, let's begin. Okay, so hi guys, welcome to the post contest discussion of the Leetcode Biweekly 141. I'm Abhinav, and let's get started with the first problem. Okay, so in the first problem, you are given an array nums consisting of n prime integers. You need to construct an array answer of length n such that each index I, the bitwise OR of answer I and answer I plus 1 is equal to nums I. Okay, so basically what the problem states is that you are given an array nums where every element of the array is an prime number that's given, and then you need to construct an array answer. So in answer array, for every index, if you have nums I, then for answer I should be such that answer I bitwise or with answer I plus 1 would give you nums I. That's what you need to make sure for every index I. Also, you must minimize each value of answer I in the resulting array. If it is not possible to find such a value of answer I, then you will store -1 in that answer I. Okay, and I hope you know what a prime number is. So you can see for the first case for 2, there was no possibility of any such number, so that number or with a plus 1 of that number gives you 2. So you got a -1 in this. Okay, so you can just try, even if you 0 or 1, that would be 1, 1 or 2, that would also be 3. Okay, you cannot get a 2 by or of two consecutive integers, so there's a -1. For 3, you can get 3 by using 1 or 2. So in numsci you have stored 1, so that 1 or 2 would give you 3. Same way for 5, 4 or 5 would give you 5. and 3 or 4 would give you 7. Okay, let's understand better here. So for the first test case, if you analyze, then for 2 our answer was -1, because we needed to find a number, so that if my number is x, then I have to make sure that x or with x plus 1, this should give me this number nums I. So there was no x such that the or with x plus 1 gives me a 2. So for this my answer was -1. Now for 3 I can get a 3 using 1 bitwise or with 1 plus 1 2. So if I take x equal to 1, then bitwise or of 1, which is 0001, and 2, which is 0010, the or of these two is going to give me 0011, which is going to give me 3. So I know for x equal to 1, I can have x or with x plus 1 giving me 3. So for x equal to 1, I can make 3. So my answer was 1 for this. Now for same way for 5, I can make 5 using 4 or 5. Okay, so if you see, 4 is basically in bitwise form 00100, and 5 is this. So bitwise or of them is going to give you 5 only. So 4 or 5 is going to give you 5. So for x equal to 4, you obtained 5. For 7, my answer was 3, because 3 or 4 is going to give me 7. Now we also need to make sure, for 7 there was one more possibility. You could have also taken 6 or 7, or yeah, I think 6 or 7. That would also give me 7. If you see, 6 is basically 1100, and 7 is 11. Okay, 110, this is 6, and 111 is 7. So there or is also going to give me 7 only. But so taking x equal to 6 was also fine here, taking x equal to 3 was also fine here. So which was the minimum among 3 and 6? It was 3, so we took 3 here. Okay, so that's what we need to find out for every basically for every test case. For every nums I, we need to find such an x, minimum x, so that x or x plus 1 gives me the nums I. Now for the first problem, if we look at the constraints, okay, the first and second, both the problems are the same. The only difference is in the constraints. Okay, so if we look at the constraints of the first problem, it is the length of the number is up to 100, and you can see nums I is up to 1000. So if you just do the brute force approach, which is basically for any nums I, just start with 0. Let's say start with x equal to 0. If you have, let's say nums I is 7, then just start checking with x equal to 0. Can you have 0 or 1 is equal to 7? If yes, then x equal to 0 is okay. Then try x equal to 1, try x equal to 2. Same way, just try all the possibilities. At max, you would have how many possibilities? If you go beyond 7, okay, if 7 is the number and you take some x greater than 7, then for sure you know x or x plus 1, this thing is always going to be greater than equal to x. Can I say this? Because whenever I do the or operation, bitwise or operation, the bits are going to get set. So when we do or operation of any two numbers, if you know the property of or, then it is greater than or equal to both the numbers. So it's greater than equal to x plus 1. So we know if we have a number 7 and we take any number greater than 7, we are not going to obtain 7 from that. So our x is going to be in the range from 0 to less than 7 only. That's only the range that we need to check. If we don't get something in that range, then we can say that we would print -1. Okay, so for every nums I, the values are up to 1000. So we can, at max, we would have to do 1000 checks for every number, and the length of array is 100. So just the brute force technique would give me an overall time complexity of 100 into 1000, in which is 10 to the power 5. So which would be well accepted for the first problem. So with the constraints of the first problem, I can just do a brute force approach. That is, for every I, just check which is the, just for every I, what we would do. So for every I, just check, like find, let's say nums I is our number. So for this, just check for every j from 0 to nums I. So we'll run a loop for every like x from 0 to nums I. We run a loop from 0 to nums I. If we find some x such that x or x plus 1, if this is equal to nums I, whenever we find such x, we'll just store that x, push that x into our answer, and we can just break out of the loop. Okay, that's what we can do for that. For every I, this x would be our answer. If we don't find it, then -1 would be our answer. So that thing we can just do for every basically I and store it in our answer. That way we can just compute using a brute force approach. Okay, so for this brute force approach, like I'll just show you the code quickly, then I'll move to the second problem. So I'm going to every value in my nums, and I'll just check. Okay, here I have written if I is 2, then we get a -1. Otherwise, for every other number other than 2, if it is a prime number, we know it would be an odd number. I'll come to the explanation why. We won't get a -1 other than 2. Okay, so only for 2 we can get a -1. So I've done that -1 case separately. And for all other numbers, we'll just do a brute force approach and check. If j satisfies the condition, we'll push j into our answer vector and break out of the loop, and we'll return answer. Okay, so the brute force approach was fine. Let's see the second problem where this brute force approach is not going to work. So we'll have to find something better approach. Okay, so if you look at the second problem, here the constraints are the length of the number is 100 only, but nums I is up to 10 to the power 9. So if we do a brute force approach going up till nums I, that would take a time complexity of 10 to the power 9 into 100, which would be 10 to the power 11, which won't be accepted for sure. Okay, so for this we need to optimize this approach. Okay, now let's try to analyze how can we optimize this. Okay, so basically for every nums I, let's denote like I'm denoting nums I by y. Okay, so first of all, this nums I is independent of other indexes. Like if you have an array nums which has many values, so for every value we would have a corresponding answer. Okay, they would not depend on other values in the array. Okay, so for every value in our array we can compute our answer independently. That's the first thing. Okay, so if we have a nums I, I'm denoting it by y. So for this y, we need to compute our answer, basically the smallest x such that x or x plus 1 is equal to y. Okay, the smallest x such that this is equal to y, and we know that this y is a prime number. That's also given in the question. Okay, we were ignoring this thing, but now we know this is a prime number. Now for a like one thing you can basically notice, whenever we do x or x plus 1, what is happening if you analyze bit by bit, because now we know the brute force approach of going checking for every x from 0 to y, this is not going to work because y is up to 10 to the power 9. So this brute force approach is not going to work. So we need to find the answer in some basically some optimized way. So what we can do, let's try to analyze this thing, x or x plus 1. What is that? If we write x in basically in any binary form, let's say x is something like this. Let's say x is something like this. What would happen when we add x plus 1 to, we do a bitwise or with x plus 1? If x is something like this, what would happen when we add a plus 1 in binary? If you know, then we go to the least significant bit. If this is 1, so if we do a plus 1 in this, what would happen? This was the least significant. If we do a plus 1, this 1 would become 0, a carry of 1 would be obtained. Then this would become 0, a carry of 1 would be obtained. This would become 0, a carry of 1 would be obtained. This would become 1. After that there would be 0 carry. So this, all these numbers, they would be copied as it is. Okay, so these numbers would be copied as it is. Okay, so whenever we perform a plus 1 to any binary number, what happens? From LSB, if we have some consecutive ones, all those ones would become 0, and the first 0 that we get, that would become 1. So basically up till here all the bits are flipped. That's what happens when we do a plus 1. Now when we do a bitwise OR of this with this was my x and this was my x plus 1. When we do a bitwise OR of both of these, now for all these bits they are the same, so their bitwise OR would also remain the same. But for these bits, now since they are flipped, so we know if there's a 0 there's a 1, bitwise OR would become 1 1 0 1 1 1. So basically for all these bits we would have all 1 1 1 1. Okay, so this was my x, this was my x plus 1. So my x or x plus 1 was, okay, 0 0 1 0 0 1. This whole thing remained the same. After that all these bits would become 1 1 1 1 1. Okay, so what happened when we have a x, what is x or x plus 1? The least significant 0 that we get, that would be converted to 1, rest remains the same. Can you understand? Like for any number x, we can say that the least significant 0 that we have, that would be converted to 1, rest all remains the same when we do x or x plus 1. That is only going to happen because whenever we do a plus 1, if we have some whatever the least significant 0 is, we would have a 1 there, all of them would become 0, rest remains the same. So these all would remain the same, this 0 or 1 would become 1, and because of these ones they would remain 1. So we can say that for any x, basically now what we need, that this x or x plus 1, this should become equal to y. That's what we want. This should be equal to y. We need to find the minimum x so that we obtain such a y. Now if we want to have this y, what is the minimum x through which we can obtain this y? Okay, so for that, what we can say, if we have some consecutive ones, we can just replace any one by a 0. Let's say we replace this one by a 0 and we have this number. Okay, this would be number. So if we have some consecutive ones initially in my y, then I can just replace any one by a 0, and if we take this as a x, then this when we do OR with x plus 1, this 0 would be replaced by 1 and we would get back y. So we can just replace any one of the ones or any one of the ones by a 0 to convert my y to a such an x which on or with x plus 1 is going to give back y. So if we try to reverse this operation, then to obtain a y, what all x can we take is make it 0, this is one possible x we can take, or make it 0, this is one possible x we can take, or make it 0, this is one possible x we can take. What is the minimum among these possible x? Okay, so this was one possible x that we could have taken, or I could say that this was also one possibility. Okay, or making a 0 here was also a possibility. 0 0 here was a possibility, 0 here was a possibility. I am considering these are the same. Okay, these were the possibilities. What if we keep all these ones as 1 only, and then basically after this if we replace some other 0, then when we do a bitwise OR of x with x plus 1, this 0 would be replaced by 1, so we won't get a y back. Okay, so I hope you understand that until we get a first non-zero. Okay, so in our y, if we move from the right, until we get the first 0, before that we can replace any 1 by a 0. If after this, if we replace any other 1 by a 0, this x is not going to get me y back because this 0 would be replaced by 1, which would be some other number. Okay, so I hope you understand that if we have some consecutive ones initially in my y, we can replace any one of them to get a x which is going to give me back y. So which is the minimum among these? Among these, if you see, which is the minimum? The minimum would be if we have a 0 at the most significant bit, because if we compare all these numbers, if we have a 1 at this bit, the other bits doesn't matter, these numbers would be greater than this number for sure. Okay, so the minimum number would be when we replace this 0 with the most significant one we can replace with. So what we would do is just move from the least significant bit. Whenever we get the first 0, the one just immediately to the right of this, replace that with a 0, we would get our minimum x, which is going to give me a y. I hope you understood what I am doing. And when would be a -1 case? Like for 2, if you see, 2 was this. Now if we try to find the first 0, the first 0 is this, and the one just to the right, it doesn't have a 1 just to the right, so we cannot replace any 1 with a 0. So whatever x we take, we cannot get this number. So for this we would have a -1. Basically for any even number, if you have a 0, all even numbers would have a 0 starting bit. So all even numbers, we can say for all even y, we would have -1 as our answer. Now in the question it was given that y is always prime. So a prime even number, only 2 is the only even number which is prime. So only for y equal to 2 we would have a -1 case. For all other numbers, all other prime numbers are odd, so we would not have a -1 case for any other numbers. Okay, so basically what we can say is, if we have y equal to 2, give -1 as the answer. Else just iterate on the bits of y from the least significant bit. Okay, so if we have this, just iterate from the least significant bit until you are getting ones. Just keep moving. Whenever you get a 0, the bit just before that, replace that one with a 0. If you just flip that one with a 0, we would get our minimum x, which is going to give me a y. I hope you understood the logic what we are doing. So how we are going to basically apply this thing is, like, I'll show you in the code how we are doing this. Okay, I hope you understood the logic, why we are doing this. Okay, when you try to add this x or x plus 1, you would know that basically when whatever x you have, the least significant 0 would get replaced by 1. So to convert a y to a minimum x, we can change any of the 1 before the least significant 0 into a 0. So what's the minimum is, if we replace the most significant 1 with a 0, that's going to give me the minimum x, which can be converted back to y using x or x plus 1. I hope you understood. Let's look at the code. To If you have any doubts in this, you can ask in the chat. Okay, let's look at the code of this to understand how I'm implementing this thing. Okay, so first thing is, I'll go to every I in my nums array. If I is 2, then in my answer vector I would push back -1 and continue. Okay, so I know for only for I equal to 2, this I is basically y that was I was telling there. Okay, the elements of my nums. So if my element is 2, for that my answer is going to be -1. For all other cases we can have some answer. Okay, so for 2 I'm handling separately. Continue. For all other cases, I'm going to every bit. Okay, I know all the other numbers are odd, so the 0th bit is going to be 1 for all the odd numbers. I know, like, for any odd number, if you take the least significant bit of an odd number is going to be 1. So if I have to get the bits from least significant to most significance, what we do, if you have studied bit manipulation, so we take a j. If j is 0, then we are trying to extract the 0th bit. That can be checked using, if I have a y whose 0th bit I have to check, then y and 1 left shift j. If this thing is greater than 0, then we would say that the bit is set. If this thing is greater than 0, we would say that the bit is set. Else, if this is equal to 0, we would say that the jth bit is unset. Okay, that's how you check whether a jth bit is set or not in a number y. Okay, if you're what I'm doing, I'm shifting 1 left shift j is going to give me the jth bit. And if I'm doing a bitwise and, if that bit was unset, I would get a 0. Okay, that if j was this, then I have a 0 0 1 0 0 0. This is 1 left shift j. And if I'm doing an and with this, if this bit was 0, then I would have a 0 completely. and if this bit was 1, I would have some positive number. So if I have get some positive number from this, I would say that z bit is set, otherwise unset. Okay, so I'll start checking from j equal to 0. So now for j equal to 0, I know the 0th bit is set for any odd number. So I've started to check with j equal to 1. Okay, so in my code, I've started to check with j equal to 1 up to j equal to 31, because 2 to the power 31 is going to cross 10 to the power 9, the range given. So at max, we can have 30 bits in our number if range is 10 to the power 9. So I'm checking from j equal to 1 to 31, going from least significant to most significant. If I and 1 left shift j, okay, so if the jth bit is set, we do a continue. Okay, so I started to check from this side. If the jth bit was set, we do continue, move j forward. Okay, until it is set, we move j forward. Whenever we get that this jth bit is unset, we'll uh, flip the j minus 1th bit. Okay, so the first j where this jth bit is unset, we would flip the j minus 1th bit. That's what I'm doing. Okay, so I'm doing a continue if this jth bit is set. Now whenever I don't do a continue, it means this jth bit was not set. I'll push back in my answer I XOR with 1 left shift j minus 1. So in order to flip a bit, we can do XOR with 1 left shift j minus 1. This is going to flip my j minus 1th bit from I. Okay, so my j minus 1th bit was 1, it's now 0. Okay, so that is going to give me the x, my minimum x, which can give me an I. So that I would push into my answer and break out of the loop. Okay, I hope you understood the implementation of this and the logic of this, and we'll return our final answer. Okay, if there is any more doubt in this, you can write, or you can move to the next problem now. Okay, I hope this problem is clear to you now. So we can move to the third problem. Okay, so in the third problem, you are given a string source of size n and a string pattern that is a subsequence of source and a sorted array target indices that contains distinct numbers in the range 0 to n minus 1. Okay, we define an operation as removing a character at index idx from source such that idx is an element of target indices. Pattern remains a subsequence of source after removing the character. Okay, so if you read the problem, I'll explain you what the problem states. Okay, let's take this test case and I'll tell you what the problem is trying to say. Okay, so basically what is given as an input, you are getting three things. First is a source, which is a string of size n, you can say. Okay, then there is a pattern, which is also a string, which is less than the size of the source, less than or equal to n. Okay, this is of size n, this is less than equal to n. And a target indices, this is a array of integers, okay, which contains integers from 0 to n minus 1. Okay, so basically what it says is we have a source. Let's say this is our source. Okay, that means we are given this string. Now target indices is 0 1 2. So if we do a zero based indexing of this our source string, then all those indices which are coming in the target indices, you can mark them that these indices, they can be deleted from the source. That's what this target indices just denotes. 0 1 2, that means these 0 1 2, we can mark them that 0 1 2, these can be deleted from the source, but those not present in the target indices array like 3 and 4, they cannot be deleted from the source. Okay, that's one condition. Then the condition for deleting is you are given a pattern. So initially you are given that for this source, this pattern is a subsequence for sure. You can see ABA, like there are multiple ways to get a subsequence ABA from this source. Now you have to delete some elements from this source such that after deleting the remainder string is also contains this pattern as a subsequence, and you can only delete these indices, and you need to delete the maximum number of indices. Okay, so you need to find the maximum number of indices you can delete, so that it still has this pattern as a subsequence, and you are only allowed to delete these indices. That's what the question states. So for this test case, what was my answer? So I could have deleted, I can delete only these three indices. So I can, if I delete this a, what would happen? If I delete this a, do I have ABA as a subsequence in this? No, we can have BA, but after A, we don't have a B to have ABA. So we cannot delete this A. I hope you understand, because if we delete this A, then the remaining string would not have ABA as a subsequence. That's the first thing. Then if we try to delete this B, okay, so if we delete this B, then you can see this ABA, we can still obtain a subsequence ABA, and there is no problem. So we can delete this B. Can we delete this B? Okay, let's say we deleted this B. Okay, what we obtained is A, this B got deleted, B, A, A. Now the indices are not going to change. If it is deleted, these are not going to move to the left. Their index would remain the same. Okay, so we can assume there's some empty thing here. Okay, there's an underscore here, we can assume. So this is my remaining array after deleting this B. Now from this, can we delete anything more? Okay, we have already deleted this. We know we cannot delete this A. When here, if you try to delete this A, we would not have ABA remaining. So only deletion that we can do is this. If we delete this B, now we have AAA. Still we cannot get a ABA. So we can only do one deletion in this case. Now what if we deleted this B to start with? We could have also deleted this B. Then we would obtain AB underscore AA. Okay, this is what we would obtain if we delete this B. Okay, this was another way. After this, again, only this B can be deleted. If we delete this, we would have AAA, which is not a subsequence. So we can either delete this B and obtain this, or we can delete this B and obtain this. That's the maximum we can delete. So a maximum of one deletion in both the cases. So my final answer is going to be 1 for this test case. I hope you understood. We could have deleted these A also, but it was not in my target indices, so it is not allowed to be deleted. Okay, so I hope you understood the problem, what the problem states. Now how can you find out what's the maximum number of deletions you can make? Okay, so let's look at the constraints of the problem. So in the constraints, this n, the length of the source, is given 3 into 10 to the power 3, and all the remaining pattern length is less than n, target length is less than n. Okay, so n is 3 into 10 to the power 3. So we know n is less than equal to 3 into 10 to the power 3. So what all time complexities can we have? So you know, you can run something of O of n square, that would be 6 into 10 to the power 6. That would be fine with this constraints. You cannot run an O of n cube, that would be 9 into 10 to the power 9. So this you cannot do, but you can definitely do an O of n square here. Now if you can do an O of n square with the constraints only, sometimes you get an idea of what you can do, like, and with this only, you maybe you would have got a feel that we can use DP here. Like you can try some greedy approaches for this. How can we do that? But any greedy approach was not exactly working, and like with the constraints only, if you can do something in O of n squares, and you have a source and a pattern. Source is of size n, pattern is something less than equal to n, at max that would be n. So we can take a 2D DP of n into n, one denoting the indices in the source and one denoting the indices in the pattern. So I hope with the problem and constraints and all, you would have got a feel of that we can apply DP here. Okay, if you didn't got a feel, no problem, just try using DP. Okay, now let's try to think with DP, how can we do? Now the most obvious thing, if I'm going to use DP, what states, like with the first thought, what states come to your mind? Okay, as I told you, you have a source of size n and a pattern of size m, you can say. Okay, let's say the size of the pattern is m. So or you would have also done DP in some longest common subsequence. These I hope you would have studied about them. There also we do something like this only. You had to make sure that this subsequence remains. So something LCA types thing we are going to do in our DP approach. that feeling you would have got if you have studied about LCA and all these standard algorithms. Okay, so what we can do, what basically what state can you take for the DP is, if I am taking a DP ij, that means I would take a state I for the source, which would denote if I is here, then for this substring, that's what this I denotes. And if I have a J here, then it's denote J in pattern. Okay, so J is the index of pattern, I is the index of source. Okay, so that's the most general state that we take if we have two things. Okay, one denoting the index of the first thing, another denoting the index of the second thing. Okay, let's try this state and check if we can write the transition for that. Okay, so whenever you apply DP, you have to make sure that the state you select, that would depend on whether you can write a transition for that state or not. That's what you have to keep in mind. So always think of the transition first. So to write the transition, if you can take some state, then take that state and write the transition. Okay, so in the mind you have to think whether you can write the transition for this, accordingly take the state. Okay, so like with the guessing, what I have decided is I'm going to take a state where my I is going to represent my index in the source, and J is going to represent index in the pattern. So with index, what I mean, if I have I this, then either I can have this substring or maybe something from this side. Let's try to have move from this side only. Okay, here also we'll move from this side. Okay, so what DP state I am going to take is my DP ij is going to, always in my return value of my DP state, most commonly we store the answer that we are going to obtain. So what's the answer that we are trying to obtain is the maximum number of removals. Okay, that's the thing that we are trying to calculate, maximum number of removals. Okay, so that only we would store in my DP state, but with ij that would constrain it to maximum number of removals for if we have the source from 0 up till I. Okay, if we have only this source as my question and this pattern from 0 to J as the question. Okay, so if the question was just the source from 0 to I, if only that much was given, and just the pattern from 0 to J, only that much pattern was given, then what's my answer that I'm going to store in my DP state? So that the, if I can write a transition and calculate this, then my final answer would be just the DP of n minus 1 and m minus 1. Okay, that would be my final answer if we have a state like this. Okay, I hope you understood the state. Now the main thing is, if we can write a transition for this, then only we'll take this state. Okay, so if we take a DP state like this, then my final if we take a DP state like this, then my final answer would be this. Now can we write a transition for this? Let's try to write the transition for this DP state. Now for transition, what we can say is, if we have a DP ij, okay, now okay, let's say we have a string s. Let's say this is my string s and this is my pattern. Let's say something like this. Okay, now if I'm writing my DP ij, through that I'm denoting if I am at some index I. So this is my source for this index I, and if I am at some index j, this is my pattern for this j. So I need to write this in terms of I minus 1 and j minus 1. Like that's what we do in while writing my transition. Okay, so if we have some letters, let's say this is my I and this is my j. If these two are same, okay, if these two characters are same, that means, okay, now I only have two options for any I. Either I would remove it or not remove it. These are the only two options. So whenever we write a DP transition, that's what we take into consideration, whether we are going to take it or remove it. Okay, so let's take the case when we are going to take it, we are not going to remove it. So if we are not going to remove it, then if this index is the character at this index is matching with the character at this index, so the thing that we need to make sure is this pattern is occurring as a subsequence in this. So if we are taking this, then I can say these are matching, so I just need to have this much to match up with something from this. So I can say if s of I is matching with the pattern of j, then I can write my one possibility of my dp state is I'm going to take it. So I'll check for dp I minus 1 and j minus 1. So basically if I'm going to take it, then for the remaining I'm not removing anything from here. So what's the maximum removals I can get for this is in this and this, the maximum number of removals I can get. That would only be my maximum number of removals for this also. And if these two characters were not same, then what's the case if I'm taking it? If these two characters were not same, then basically I also need to match this with somewhere around this. Okay, so then I would have dp I minus 1, okay, with j, because now the jth index is not matched up. Okay, so for this if case I had this, and for the else case I would have this. Okay, so depending on this if else, this is my one of the possibility if I am going to take it. Okay, so this is my take case. Now if I am going to remove it, so this is one case. If I'm going to take it, then either this or this, depending on my si is equal to pj or not. And if I'm going to remove it, then what I can say is, first of all, I would have to check whether I can remove it. So if this I is occurring in my this array, the target indices array that I was given. So first thing, in order to optimize this checking, what I would do, I would create a vector of a boolean vector having n indices. I would just mark it which all indices are movable, which all indices are removable. Okay, so like here we can mark all the indices as 0 0 0 initially, traverse through this array. If we have a 0, mark it as 1, 1 mark that as 1, 2 mark that as 1. So I have marked that these three indices are removable, rest are not removable. That I can do initially only. So let's say I have an array of check, okay, where this check I is going to store 0 or 1. 0 denotes it's not removable, 1 denotes it's removable. Okay, so let's say if I have a check array, so if this check is 0, then only the take case is going to occur. If this check is 1, then I can remove, then my not take case is going to happen. So if the check is equal to 1, then only not take case is going to happen. Now for the removal case, what would happen if I remove this ith index? If I just remove this ith index, basically I have to manage till this j using this much. So I minus 1 and j, that dp state, and one removal we got, so a plus 1. So we can write for this, we would have 1 plus dp of I minus 1 and j. This state we can write for a removal case. Okay, so I hope you got the dp transitions, that when I'm taking it, I would just check if si is equal to pj, then write this, else write this, and when I'm not taking it, write this. Now take the minimum or the maximum of the two cases. Okay, so my final dpij is going to be max of this case or this case. And if this check was 0, then this case is not happening, so only this one would be my transition. So I hope we can write the transitions, so you would have understood that yes, we can write the transitions with this state. So my dp is going to work, and we can just get the final answer using this. Okay, is there any doubt in this? Okay, this overall is my dp transition. This is the DP transition, and this was my state. What would be the base case? One more thing that we need to write our code is the base case. So what would be our base condition is, I can say if we have a DP, like if we have this I is empty, let's say I have not, I am at index -1, let's suppose. If this I is empty, 0 was the first index. So if I have not moved to anything and this pattern is also empty, then I can say that dp of like -1 comma -1, this is going to be how many removals. This is fine if we don't have anything and we don't have anything in the pattern that is going, we should make, then this thing is going to, like this is fine, but we are not removing also anything, so a zero removal. So this, I hope you understand, this would be my base case. And whenever I am moving ahead and this pattern is still empty, then if this check is 1, I can remove it, otherwise not remove. Those would be considered in my transitions. So I think only this one would be my base case. And one more thing you need to consider here is, what if you have some dpij where you have till this I and you take till this j, but you cannot get this pattern as a substring in this. So that case can also happen because I'm analyzing all the states of my dp from I is going 0 to n, j is going from 0 to m. All the states are getting analyzed. So a state may happen where this string does not contain this pattern as a substring. So that we can denote the answer for that dp, we can denote by a -1, let's say. Okay, so that thing we would have to consider while taking my transitions is that if any of this dp, that we can also have a -1 in our answer, that in the state I can show maximum number of removals this, if it was possible, or here only I can write if p of 0 to j is not occurring as a, is not a subsequence in s of 0 to I. Okay, if this is not occurring as a subsequence, I would have a -1 for that dp state. Okay, that I'll denote with -1, that this state cannot exist. Basically you cannot have that. Okay, so if we have some this state in this, our in our transition, we'll not use it. Okay, so here again we would check if this dp I-1 and j-1 is -1, then we'll not take it, or we'll assign ij also -1. And again from this state also, if this I-1 j is -1, then we won't do a -1 plus 1 and make it 0. This would again, this overall would be -1 only, because if this state cannot exist, we cannot write a 1 plus a state that does not exist. So we'll also have to check whether this state is not -1, then only we will write the state. Okay, so I hope you understood these extra cases we would have to handle in our code, the -1 case. Okay, and my base case was dp -1 is, okay, dp -1 is 0, and that I can write as a base case. Or one more case I can write is, if we have some I and my j is -1, we don't need to consider anything, any pattern, so we can just write it as, I think that would be considered in my transition, but I have written in my code for extra safety, so I'm just explaining that, that if my dp I -1, if I'm computing that j is -1, it means we do not need to make sure anything, that this sequence is occurring or not. So we can just write it as dp I -1, that number of removals till I-1, and then this can be removed if the check is 1. So plus check of I am writing. If the check of I is 1, then we get a +1 removal. If this is 0, then we don't get a removal for this ith index. Okay, so this can also be considered as a base case if we have j -1. Okay, so with these base cases, I have written. And one more thing, if this I is less than j, then I can make it -1. Like if j is more and I is less, then we can never have a substring of length which is more than the length of the string. So if j is greater than I, you can understand the state would always be -1, that we cannot have a basically, if you have a length of my substring is j, length of my subsequence is j, that cannot occur in a string of length I which is less than j. So for this case my answer would always be -1. So these would be my base cases. Okay, I hope you understood the base case, the transition, and the state. So we can move to the code to understand better. How can we use this LCS to solve this? This is basically kind of LCS only. If you look at the code of the LCS, longest common subsequence, there also we take a state like this only, where we try to make a subsequence. So either we take the element or not take it. There we are maximizing the length of the subsequence that we take. Here we are basically minimizing the length that we are taking. We are maximizing the number of removals. So maximizing this you can consider as a smallest common subsequence. So I think the problem is the smallest common subsequence only is the problem. Just making sure about this extra check functionality, the target indices thing. Okay, these some extra things you have to make sure. The extra edit you have to do in your LCS code only, and it would become the code for this problem. Okay, I hope you understood. Now we can move to the code. Okay, so if you look at the code, what I'm doing, this is my DP function, the I've written a recursive DP. So what things I have the states as I and j, and I'm passing these check, the source, and the pattern, these three as a reference. This check I have created initially, like you can see. This check is a length n, vector of int or vector of bool also you can take. All are initially 0, and then I'll move to every value in my target indices, and I'll convert that index to 1. Okay, so in my check function, in my check array, basically my check I would be 1 if I is present in the target indices, and it would be 0 if it is not present. So through this I'm making my check array that I would use to check whether I can remove this ith index or not. Okay, so now I'm taking a dp of n into m. I'm initializing it with -2 because I know -1 is a actual value of my DP. So to do the memoization thing, we need to take some value which cannot be the value of the DP. So if you have all positives, we take -1. But here -1 is a valid state of my DP. So I'm taking I'm sorry. So I'm taking -2 as a state for memoization. So I'm initializing my DP with -2. So here you can see during the memoization part, if dpij is not -2, I would return dpij. Okay, so I'm doing the memoization thing using -2, and then these are the base cases. So if j is greater than I return -1. This was one base case that I wrote. J is greater than I return -1. Then if I is less than 0, then I return 0. This case dp -1. So if I is less than 0, I would return 0. And then if j is less than 0, basically when j is -1, then what I wrote, dp I -1 plus check I. So func of I -1 plus check I. Okay, so these are the base cases that I wrote. I did the memoization, then I have to write the transition. So for transition part, we had to take two cases. If si is equal to pj, what would happen? For the take case, we take dp I -1 j -1, and for the removal case, in this it's the same for both. Okay, so basically if si is equal to pj, we take this, otherwise we take this. So if si was equal to pj, we take func of I -1 j -1. Okay, basically dp of I -1 j -1. Else this thing, these two things I have combined in. You can write like this only, what I have written. Like in my code, what I have done is this I -1 j, in this we would do a +1 if this check I is 1. If this check I was 0, we would not do a +1. So I have combined these two things and written it as dp I -1 j plus check of I instead of 1. So if check I is 1, it would be 1, otherwise it would be 0. So like you can see, if this function, basically this dp, if this dp was not minus 1, so if this I minus 1 j was not minus 1, I have written dp ij as func of I minus 1 j plus check I. Okay, so dp of I minus j plus check I, it would be 1 here and 0 here. Okay, this thing I have considered if my this dp was not minus 1. Now uh, and with the initialization part, I have just taken this equality case. If this was equal, I would take dpij as this to be initially, and if they were unequal, I would take it as minus 1 initially. So initially, if they were equal, I would take I minus 1 j minus 1, else I would take minus 1. Okay, so like the order of writing these if else cases can be like, you can, by your understanding also, you can write like, while explaining I did in this way. So if I would write in this way, then I would do a if condition here, if else I would write this, and then I would maximize it with this. But while writing the code, like, I hope you understand that both the things are the same. From this I converted and wrote that if si and pj were equal, I would have dp I minus 1 j minus 1. So if they were equal, I would have dp I minus 1 j minus 1. Otherwise, this I minus 1 j I'm considering after it, else I'm writing minus 1, and this is moved in this side. If check I is 0, we would have a plus 0. Okay, so there I have written minus 1, and then here I have written that plus check I. Okay, so if check I is 0, it would automatically become 0, and this case would be handled here. So I hope you understood the transitions, and then we return dpij. So this was my recursive function for my dp, and in my actual function, I've just calculated my check using this, which I explained you earlier, and in my dp I'm assigning n into m minus 2 initially. For memorization, we would return dp of n minus 1 m minus 1. That was my final answer. As I explained you there, what's my final answer? Dp n minus 1 m minus 1. So func of n minus 1 m minus 1 was my final answer, so I returned that. I hope you understood the code for this also. Okay, what would be its time complexity? We are taking a 2D DP of size n cross m. This n is max 3 into 10 to the power whatever was written, 3 into 10 to the power 3. This is my n, and m is also up till n only. At max it would be n. So basically the overall time complexity I can write is, my dp states are n cross n, so order of n into n, and my transitions are all order of 1, so no extra complexity for my transition. So n into n is my state, so n square is, you can write, say, n of n square is my time complexity. And if you talk about space complexity, that would be uh, order of n square only, because you are taking a dp which is n square sized vector. Okay, so I hope the third problem is clear to you. If there is any more doubt in this, you can ask in the chat, or we'll move to the fourth problem next. Okay, I hope this problem is clear to all of you. We can move to the fourth problem now. Okay, find the number of possible ways for an event. You are given three integers n, x, and y. Okay, an event is being held for n performers. When a performer arrives, they are assigned to one of the x stages. All performers assigned to the same stage will perform together as a band, though some stages might remain empty. After all performances are completed, the jury will award each band a score of 1 to y. Return the total number of possible ways the event can take place. And return the answer modulo 1 in 9 plus 7. and two events are considered different if any performer is assigned a different stage or if any band is awarded a different score. Okay, so I'll explain you what the problem is stating. Okay, we have three integers n, x, and y. We are given three integers n, x, and y. What does that mean? That there are n performers. Okay, so you can consider there are n different people, there are n performers. Now, and there are x stages. Okay, x are the number of basically stages that are there. Okay, so and okay, so there are n performers. You can say 1 2 3 4 up till n. Okay, there are n performers. Okay, I'll show you. There are n performers and there are x stages. Now every performer in this, like, there are n different performer, so every performer would be assigned some stage. Let's say the performer number 1 is assigned stage number 2, performer number 2 is assigned stage number 1, performer number 3 is also assigned stage number 2. Okay, so every performer is assigned some stage. Let's say something like this is happening. Okay, now what would happen? For every stage there would be some number of performers that would be assigned to that stage. Okay, so all the performers assigned stage number 2, they would form a single band. Okay, so you can consider they are in a single group, they would perform together. So if 1 and 2 both are assigned stage number 2, they would perform together. Now we are also given a y. What does y means? That every band would be given a score from the range of 1 to y. Okay, so after the performances, so first, let's say for stage number y, there are some number of people who performed at stage number y, stage number 1. So after their performance, all the group of those people, they would be given a score from 1 to y. So either they would be given a score 1 or a score 2 or a score y. That is the score given to every performer from a stage. So okay, stage number 1 would receive a score from 1 to y, stage number 2 would receive a score from 1 to y. Okay, like that. Now after the performances, after the scores are received, you need to find. Okay, so there can be multiple ways in which every performer can be assigned stages, and then after they perform there can be multiple ways in which they can be assigned scores. Okay, so finally there can be multiple ways of doing it. Let's say through some one particular assignment and one particular score assignment. Okay, that is called a single performance, a single way of performance. Now two different like two different performances would be different. Okay, what's the definition of two events? Okay, so one event is basically they are assigned some stages. Okay, and every performance, every band is given some score. This whole thing is considered a single event. Now there can be multiple ways of this event happening. So two events are considered different if either one of the things happen. Any performer is assigned a different stage, then the two events would be different. Or if any band is awarded a different score, then also the two events would be different. Now you just need to find the number of ways in which events, the number of possible ways the events can take place. How many different events can we have? That's what you need to find out. Okay, so this is a problem of basically you have to just apply the permutations, combinations, and calculate this. You have to do the maths basically in this. And if you look at the constraints of the problem, they are n, x, y, all are up to 1000. Okay, so the constraints is like this: n, x, y, all are up to 1000. So basically you can do something of the square of 1000. Okay, you can do something n into x or n into y. Okay, you can go basically to the second power of this. You can multiply any two things, but you cannot do n into x into y or anything which is going to a cube of 1000, because that would be 10 to the power 9. That won't be accepted. So you can only go up to a square of 1000. Okay, you can have any two things multiplied there in your final time complexity. Okay, that's what we understood from the constraints of the problem. Now let's try to calculate how we can do this. Okay, so for the by the definition of different, you understood. Okay, for an event there are two things basically. First of all, every person would be assigned some stage. That's the first part. Then after they are assigned, every event, okay, there can be some event which doesn't get any performers. Okay, there can be some stage which doesn't get any performers. Okay, these are the performers and these are the stages. Okay, so let's suppose this stage number 3 doesn't get any performers. So then this stage number 3 is ignored, you can say. Its score wouldn't be considered, it won't get any score also. Okay, so a score would be only assigned to those stages which get at least one performer. That also you need to keep in mind. Now if we try to calculate, so if there are n performers, every performer has a choice. They can be assigned any stage from 1 to x. Okay, so every performer can have x options of getting assigned. So if you had to just calculate the number of ways these performers can be assigned to x stages, what would that be? Just blankly, if you just calculate that, this score thing is not there. If you just suppose only this was the question, then what that would be? For any performer there are x options, for the second performer there are x options, for the third performer there are x options. So you can see x into x into x, how many times? N times. There are n performers, so you can see x to the power n. Okay, this would have been the number of ways basically the performers can be assigned stages. Okay, that I hope you can understand, that every performer can be assigned one of these x stages. So x options for every performer, and there are n performers. So x to the power n would be the number of ways these performers can be assigned stages. But here the problem is, if among these x to the power n ways, there would be some way, let's say, where some stage number 1 is assigned all the n performers. Okay, and there would be some way where stage number 1 is assigned n minus 1 performer, stage number 2 is assigned 1 performer. So for the first case where all the performers are assigned stage number 1, there can be y number of scores that could be assigned to that. So we would have to multiply and into y to the number of events for that. But if there are two stages that are getting some performers, then for this also we would have a multiplied by y. For this also we would have multiplied by y, because if both the stage are getting some performers, for the first stage there are y options of scores that can be assigned. So if they are assigned different scores, these are considered different events. So y ways here, y ways here, so y square ways would be additionally added to our answer. Now if two stages are assigned, if three stages are assigned, then y cube would be multiplied. I hope you understand. But the problem is, if you are multiplying in this, now in these x to the power n ways, some of them would have three stages assigned, some of them would have two stages assigned, some of them would have one stage assigned. So you don't know whether it would be multiplied by y cube or y square or y to the power. If all the x stages are multiplied, it would be y to the power x. It can be multiplied by anything. If all of them would have been equal, then we would have just multiplied in this y to the power some x. But here we cannot do directly. X to the power n into y to the power x we cannot do directly, because all the stages in all the ways, it's not guaranteed that all the stages are assigned some performers. Some stages would remain empty. For that you won't do a multiplied by y for the stages which remain empty. So what you can do is, instead of, now you know for sure, if we know that among the x stages, if I of the I stages are assigned performers, if we know that if I out of x stages are assigned at least one performer, if we say that out of the X stages are assigned at least one performer, then whatever would be the number of ways of doing this, in that we can just multiply y to the power I, because for the score part. Okay, so whatever are the number of ways to assign I stages to X performers, in that if we multiply y to the power I, because for every stage there can be y different scores that can be assigned. So for every stage we would do multiplied by y multiplied by y. So if I of the stages are assigned performers, we would multiply it by y to the power I. Okay, so now what would this I be? This I can vary from, okay, so this I can vary from 1 to X, because a performer can be assigned only, it can happen that only one stage is assigned to all of the performers. Okay, then I would be 1, that only one stage is assigned to all of the performers. It may happen that two of the stages are assigned to all the performers, or three of the stages are assigned to all the performers. At max, all the X stages would be assigned at least one performer. So this, if we vary this I from 1 to X and then compute this, so then I can write my final equation, that I can say my final answer is going to be the summation from I equal to 1 to X. Okay, so we have divided this problem into cases. First case is when I is 1, that means all the performers are assigned only one stage. Second case is I equal to 2. All the performers are assigned exactly two stages. Okay, it won't be less than 2 or more than 2. So exactly there would be two stages that would have non-zero performers, more than zero performers. Rest all stages would have zero performers. I equal to 3 would mean there are exactly three stages among these X stages that are assigned some performers. So if we divide this problem like this, so we can write the sum for every I from 0 to X. If we can find for every I what are the number of ways, if we add those ways, then we can find the answer. Now what would come here? So if you have fixed your I, okay, you have fixed that among n, for those n performers, there are exactly I stages that are assigned some performers, at least one performer. There are exactly I stages that are assigned at least one performer. Now, first you would have to choose what all those I stages are. So among X, let's choose the I stages. Okay, so that would be the number of ways NCI. First thing I can write that I would, XCI. There are X stages. Among that, I would choose the I stages that would be assigned performers. Okay, now I know the I stages are fixed. Among those I stages, in those I stages, okay, let's say I is 3 and I have fixed 1 2 3. These are the three stages fixed by me. Okay, so I have to assign at least one performer to every stage from 1 to 3. Every stage should get at least one performer, and then there can be more number of performers. So what are the number of ways to assign these n performers to three stages? Okay, that we would have to calculate somehow. After that, we would multiply y to the power 3, because if there are exactly three stages which are assigned some performance, so after the performances we would do into y for all those three. So multiplied by y to the power I is going to occur. Along with that, one thing that we would have to multiply is the number of ways to do this thing, the number of ways to assign exactly I stages to n performers. Okay, so that I am denoting. Okay, so what I am telling is multiplied by number of ways to assign exactly I stages to n performers, where each stage get at least one performer. Okay, that I'm making sure all these I stages get at least one performer. Okay, this I can write as my final answer. Can we? Okay, now you need to compute this thing. How can you calculate this? Okay, this became a separate question by in itself. Now we know that for calculating this, I'm moving for every I from 1 to x. So this and this xci, the ncr we can just pre-compute, or we can just compute this in, we have to do everything in modulo m. Okay, so if we compute the factorial, if we pre-compute the factorial, we can do this in order of 1 time. We can compute the xci if we pre-compute the factorial from 1 to 1000. We can just pre-compute the factorials, then we can calculate x factorial upon x minus I factorial into I factorial. This thing we can compute in order of 1, or we would have to do the modulo inverse, so that would take order of log n, you can say. Okay, almost same as order 1. This is almost order 1. Y to the power I, through binary exponentiation we can do this also in order of log n time only at max. Okay, so these things are not going to take too much of time. This whole thing I'm doing x times. Okay, so x is 1000, so 1000 time I'm doing this. So I need to compute this thing in at max. Okay, I can go square of 1000, so in at max 1000, in order of 1000 only I need to compute this thing. If I can compute this, then I can calculate my answer. Or if I can find some way to pre-compute this also, that all pre-computation I can go in n square time. So let's try to think how can we calculate the number of ways to assign exactly I stages to n performers. Now we know there are n performers. Okay, we know the I stages are fixed. Okay, let's say 1 2 3, the stages are fixed. Now I need to assign them. Some of them would be assigned to stage number 1, some of them would be assigned to stage number 2, some of them would be assigned to stage number 3. Now if I like try to think, if the first one is assigned to stage number 1, or like in this way, when I was computing, there were I ways for every performer, so total of n performers, so I into I, n to the power I. But in that there would be cases where some of the stage is left empty. Okay, that was the problem there. You need to have all these 3 stages, or all these I stages, to be non-empty. At least one performance should be assigned there. After that, remaining you can assign to anywhere. So for this, what we would do is, we basically need to, if we have I stages, we need to divide these n people into sets of I. Okay, so also the problem was these n people are different. Okay, the one basic DP computation that would come to your mind, that you can do when these n people are not distinct, they're considered same. But since these n people are distinct, okay, person number 1, if it is assigned to stage number 1, and person number 2 is assigned to stage number 2, that is different from person number 1 assigned stage number 2 and person number 2 assigned stage number 2. I hope you understand that this thing and this thing, they both are different, because all the people are distinct there. Which people is assigned which stage, that would change the event. Okay, so since they are distinct, so we need to find out some way to basically divide these n people into I different sets, and then we can assign those I state sets to the I stages. Okay, so in order to compute this, what I'm doing is, if I have n people, I'm dividing these n people into I different sets. Okay, so there is set number 1 2, let's say I is 3. Okay, there are 3 sets. Okay, so I'm telling s1 s2 s3. Okay, so every person, okay, so there would be some group of people who are assigned set number 1, there would be some group of people who are assigned set number 2, some group of people assigned set number 3, and then these basically I sets are assigned to the I stages. Okay, so in order to divide these n people into I different sets, so if we try to write some DP approach for that, what it would be, that every person, you can say that what I'm saying is, okay, first of all, if I divide this into, let's say I find some ways to divide these n people into I different sets, then I would assign these I sets to I different stages. Okay, so if set number 1 is assigned to 1, 2 to 3 to 3, that is one way. Or 1 is assigned to 1, 2 is assigned to 3, 3 is assigned to 2, that can also happen. So if we do a factorial I, then we can find all the rearrangements through which we can assign these sets to these I different stages, because all the stages are also distinct. Okay, stage number 1 and stage number 2, they are distinct. Okay, so if set number 1, the set of the first group of people is performing on stage number 1, second group of people performing on stage number 2, if it is like this thing is different from first group of people performing on stage number 2, second group of people performing on stage number 1. Okay, so that you have to keep in mind. So when we divide these n people into I different sets, after that we need to multiply it by factorial I to assign them I different stages. Okay, so if we can compute this multiplied by factorial I would give me basically this. Okay, so how can we compute this? How can we divide these n people into I different sets? Okay, so for that what I would do is I would assume that what we need to do is we have to divide n people into I sets. Okay, let's say I denote this by dpni. Okay, dpni denotes the number of ways to divide n people into I different sets. So can we write a transition for this? Okay, what we can say is there are n people. Okay, so let's say the first person, he can go in either set number 1, set number 2, set number 3. There are I different places where the first person can go. So there would be I different ways. So there would be I different uh, ways in which the first person can be placed into any one of the set. Okay, so if I'm placing the first person is set number 1 or set number 2 or set number 3, let's say there are I different ways to place that person. Now for the remaining n minus 1 people, if I assign them into these I different stages, that would also be fine. So into dp of n minus 1 I. Okay, like through this what we compute is if I'm assigning the first person, there are I different ways to assign it a stage, and then all the remaining person, again I'm assigning n minus 1 people to I different stages. Okay, that is one way. Another thing is we need to have all the sets should be non-empty. Okay, so if we assign the first person to a stage number 1, that means I don't need any more person to come in this stage. It can also happen if the ith person is assigned stage number 1, remaining n minus 1 people can be assigned I minus 1 stages. Okay, that would also be fine. So plus I would do if remaining n minus 1 people are assigned I minus 1 stages. Okay, so what I'm doing is, one thing is the first person is assigned set number 1, and then remaining n minus 1 people are assigned the I minus 1 different sets. That is one way. Or if the set number 1 contains if the place where the first person is going has more than one, basically more than one people, then I can say that the first person is assigned some set. Okay, that can be I different sets, and then the remaining people are also assigned I different sets. Okay, so this is that case, and this was the case where the set to which the I first person is assigned is not assigned to any other person. So remaining I minus 1 sets are assigned to n minus 1 people. Or if that is still assigned to some more people, there are more than one person in the first set, then there are I different ways for this person to be assigned some set if I'm considering this one. I hope you understood this transition. Little basically maybe the doubt that would have been coming to your mind is why we multiplied by I here and not here. Okay, so if we try to analyze what our state was, we have to divide n people into I different sets. Okay, what I mean by sets is let's say I'm dividing into 1 2 4, and this set is containing 3, this set is containing 5. I have 5 people, I have divided into these sets. Okay, now I'm not considering that is one way. Or another way was if 5 was here and 3 was here. Okay, so these both are the same because I'm just partitioning the people into 3 different sets. Okay, the partitioning remains the same. 1 to 4 in one group, 3 in another group, 5 in another group. Now the order of these does not matter here. That I'm considering after I have divided them, then I'm multiplying by factorial I to change their orders. Okay, if I would have considered the order here only, then again the writing the transition was not possible in that case. I tried through that way only initially, but you can try through that way, like considering the sets as different. Then writing the transition was not becoming possible because there was some case where the considering that thing that all the sets should be non-empty, that case was missing, that some of the set may become empty and there would be repeating cases which you cannot manage. So here you can manage every case. Is I'm considering sets, not events. Okay, so sets basically mean that 1 to 4 are grouped in one set, 5 in another, and 3 in another. So if we have like this, or if we have write a 5 here and 3 here, they both are the same thing. Okay, the grouping is still the same: 1 to 4 in one, 3 in another, 5 in another. So I hope you understood what I mean by dividing n people in I sets. Now whichever is fine. Now try to understand what I'm doing while writing my transition. Is if I have n people divided into I sets, I would write it in these two terms. Okay, so if I am considering n minus 1 people and I minus 1 set, okay, basically I'm saying that the first I'm taking out the first person. Okay, so n minus 1 people are left. Okay, so I have to assign this first person into one of the sets. Let's say there can be two cases: either this first person is alone in one of the set, or it is not alone. Okay, these are the two cases, that first person, okay, whichever set that first person would belong, either he would be alone in that set or he would be not alone in that set. Only two cases can happen. Okay, if he's alone in the set, that means there is one set separately for the first person, and then rest of the n minus 1 people are divided into I minus 1 set. So this is the case. Rest of just divide rest of the n minus 1 people into I minus 1 set if the first person is alone. And if the first person is not alone, that means whichever set that person is in, it's containing more than one person. Okay, so the first person can be in I different sets. He can be in any of the I. So basically what you would do for the remaining n minus 1 people, you assign them I sets. So remaining n minus 1 people assigned are divided into I non-empty sets. If there are I non-empty sets, in that place the first person in any of one of those I sets. That is one way to keep the first person not alone. Okay, so assign I sets, divide n minus 1 people into I different sets and assign the first person any one of those I sets. Okay, so that's why there's a multiplied by I, because there are I different sets. The first person can be assigned to any one of those I different sets so that the first person is not alone. So not alone case would have I into dp of n minus 1 into I. I hope you understood this transition. So once you have understood this, that means I can compute this transition is an order of one transition. So in n into I times, I can compute for all n into I. Okay, if we divide, can we divide n people into I sets? Now in my formula, what I can do is I can replace this number of ways to assign I stages to n performers. What would this thing be replaced by? Okay, so if you have to assign n performers I stages, so dp of ni, okay, the dp that we computed there, this is going to give me if n people are divided into I different sets, and if I multiply that with factorial of I would get number of ways to assign n people to I different stages. Okay, so this whole thing can be replaced by this. So my final equation becomes, for every I from 1 to x, I would calculate this into this into this. Now this, if you have pre-computed this dp of ni, okay, so we would have to pre-compute this dp of ni in n into I times. So this I can vary from 1 to x. So we would have to pre-compute dp from dp of n into x. Okay, this thing, if you pre-compute a dp of n cross x, that would take n into x time. In that much time, I can pre-compute this. So for every I from 1 to x, I can just, in order of 1, I can write the value. Okay, so this pre-computation would take n into x time, which is okay. Then this is going to take a log n time multiplied by order of 1. So, and this is x. So x log n. So x log n plus n into x. That's the overall time complexity. If you analyze the overall time complexity, this above dp pre-computation is going to take n into x time, and then a factorial pre-computation you would have to do factorial pre-computation and order of, you would compute factorial up to 1000, and then the next thing would be, while traveling here, if you have to do this computation, this is going to take some log n time, and then this thing is order of 1. Factorial is pre-computed, so order of 1. So x times log n. So then a plus for your final answer computation, that's going to take you x into log n time, you can say. Okay, so overall time complexity is n into x only, you can say the highest is that, which is fine. Okay, this time complexity would be accepted. I hope you understood the logic. We can look at the code now. Okay, let's move to the code. Okay, so okay, so first thing I'm doing is doing a factorial pre-computation. So I have taken a global variable factorial up till 1000. So I'll just pre-compute all the factorials modulo 1e9 plus 7. Okay, I have defined my int as long and then here undefined int, so that I'm doing modem here. The product may exceed the range of integers, so it's important to use long here. Okay, so one way was you could have used long everywhere. What I did is hashtag define int long. All my int became long, and after the function I undefined int, so that in the actual main function that is written, which is not available to us, accessible to us, if that becomes long, then it would give you error. So this undefined int is important. Okay, now that thing is done. Then I've taken m as 1e9 plus 7. I had to print my answer, final answer, as modulo 1e9 plus 7. So I'm going to pre-compute my factorial. This is a global variable, and inside that I would pre-compute my factorial from 1 to 1000. Factorial 0 is 1. After that, factorial I is factorial I minus 1 into I mod m. So I pre-computed the factorials up to 1000 mod m. This pre-computation is done. Then I've taken a dp variable, dp vector, 2D vector, to compute this thing. Okay, this thing that we were trying to compute, how to divide n people into I sets, that I'm going to compute using my dp vector. So base case would be dp00 is 1. Okay, so this was the transition that I wrote. What would be its base case? If I'm writing dp0 and 0, it means I'm dividing 0 people into 0 sets. So there is one way, that just don't place any people in any set. That's not placing anything in anything is one way. So that would be the base case. So whenever I try to compute dp any I0, okay, so that would be, or whatever n0, so that would be multiplied by I and n minus 1 0. So if I compute dp 1 0 through this transition. So all of this would be covered here. dp00 would be 1, and then this would be basically okay. So all of them would be covered here. You can, like, for extra safety you could have also written more base cases like dp10. If you like, if you wish, you could have written more base cases for extra safety if you did not understand how through the transition only those would be computed. Like if you write dp10, there is one person and divided into 0 sets, there would be not, there would be 0 ways to do that, because if there is one person, at least that should be divided into any one of the sets. So you can write dpi0 as 0. Any person dividing into 0 sets is not possible, so 0 ways for that. And you can write dp0 if there are 0 people and you have to divide it into something greater than 0 number of sets, that would also be 0. That if you don't have any people, you cannot divide it into more than 0, like any number of sets. So these two base cases also you can write, but they would be covered in the transitions if you write only this base case. Okay, so I've only written this base case, and then my transition is this. Okay, so I'm computing my pre-computing this dp for n cross x. Okay, so here at max I would have n, and this I would at max go up till x. So n cross x, I've taken a dp vector for n plus 1 into x plus 1. Then dpij is j into dpi minus 1j. Okay, dpni was I into dpn minus 1. So here this is I and this is j. So it would be replaced by j here, I minus 1 here, and j here. So you can see j into dpi minus 1 j modulo m. Okay, whenever you are doing any multiplication or anything, just do a modulo m, because you have to print final answer as mod m, plus dp I minus 1 j minus 1, this dpn minus 1 I minus 1. Okay, so I have written this transition. Okay, I have done a mod m everywhere whenever I do plus or multiplication. So this way I have pre-computed my dp. Now I have to compute my final answer. What's my final answer? Is for every I from 1 to x, I run a loop from I equal to 1 to x. Then I would write answer is equal to answer plus xci. Okay, so I've written an ncr function in that. So this is xci. I'll show you the ncr function multiplied by y to the power I. So I have taken y to the power I. Pow m is a function to calculate the binary exponentiation mod m. Okay, if you directly use your the inbuilt pow function, then y to the power I may exceed the long range also. So you have to do the mod m computation step by step. So I have written my own function of pow m to do the mod m in every step. Okay, so y to the power I. After that, this thing is dpni into factorial I. So after that, dpni multiplied by factorial I. This factorial is pre-computed. In every, after every product, I'm doing a modem to make sure it's not exceeding my long range. Okay, and a modem finally also. So I'll show you the ncr function. ncr, what ncr is factorial of n divided by factorial of n minus r into factorial of r. So this modulo division is going to give me the whatever is in the denominator, it would do the modulo inverse of that. So whenever you have to do a p by q, so p multiplied by modulo inverse of q is q to the power m minus 2. Okay, I hope you know that how we do modulo inverse, because you have to compute everything in mod m. So the denominator would be converted to a modulo inverse. So I've written a mod div function. So, and this fact and factorials are pre-computed already in my fact vector. Okay, it's already pre-computed. Okay, so my ncr is going to be factorial n divided by n minus r into r. Okay, so this division is done through modulo inverse, and this pow m function is my binary exponentiation function, which I have also used here, y to the power I. So this is the binary exponentiation mod m. I hope you know how to write the binary exponentiation function. Okay, so I hope you understood. Is there any more doubt in this? So then dpni gives 0 when n is less than I. Um, when n is less than I, yeah, dpni would give you 0. Those things would be already computed here in the transitions. Yeah. That also you can write in the base case, or it would be covered in the transition only. Okay, is there any more doubts in this? Okay, so if you analyze the overall time complexity of this whole factorial pre-computation is taking an order of 1000 time. Okay, then this dp computation, we are running two loops. Inside that, this is an order of one thing, so that is taking you an order of n into x time. Okay, then in this ncr is, this is pre-computed, but modulo division is using a powm function which is log n time. Okay, so this is basically taking you a log n time. This binary exponentiation again is taking you a log n time, or log I time, you can say. Again, nca for ncr also, it's taking a log n time. Okay, so log n log I, and then this is order of 1, order of 1. Okay, overall x times. So this is basically order of x into log n. Okay, it would be log n or log x, whichever is bigger. Okay, so max of log n or log x, whatever you want to call it. I hope that is okay. So overall time complexity is 1000 n into x, x into log n. So I hope overall time complexity, the biggest one is n into x only, and plus you can write x into log n would always be smaller. So n into x is the biggest thing here. So n into x would be accepted here for the given constraints, which was 1000 for n and x. Okay, and space complexity would also be, I think, n into x dp is there. Other than that, nothing else is going taking much space. The factorial is taking 1000 space. Okay, so order of n into x, you can see. Okay, I hope this problem is clear to everyone. Okay, one doubt in question 2, why not binary search? Okay, if I move to question 2, how would you do binary search here? Because uh, there can be, like, if you analyze for a particular y, like you are trying to find the minimum x here, so there would be some x where you get a yes, but they are not consecutive. You don't have a predicate function here where you are getting 0 0 0 as your answer, and after some stage you are getting 1 as your answer. There is some stage in between, there is some x where you get a 1 as your answer. Yes, that can be done. Then again 0, then some x where you get a 1. Okay, I hope you understand. Like for this, for the 7, x equal to 3 was okay, x equal to 6 was okay, but x equal to 4 5, they were not okay. So you can see, like for this, if you try to draw, then for 7, x equal to 1 was not okay, x equal to 2 was not okay, x equal to 3 was okay, x equal to 4 was not okay, 5 was not okay, 6 was okay. So you don't have a predicate function where there is 0 and then 1. So in this you cannot apply a binary search. Like, is there any other way through which you are trying to make it a predicate function where you are applying binary search? Then tell me. Okay, is there any more doubt to anybody else? All the four problems are explained. If you have any doubts in any of the four problems, you can ask, or we would end the session then. Okay, it's clear to everybody. Nobody has any more doubts. Can we end the session? If you have any other general doubts also, you can ask. I see there are 30 people still in the chat. Okay, then bye bye, guys. I hope you liked the session. Thanks for tuning in. Goodbye.